Recrystallization, background. In this webcast, we will discuss what recrystallization is and how we utilize the solubility of a compound to perform a recrystallization. What is recrystallization? Recrystallization is a purification technique for solids that is based on controlled solid to solid phase transitions. In other words, you take a solid, you dissolve it in some solvent, and then after being dissolved, the compound returns to being a solid, hopefully in more pure form. This technique is capable of purifying compounds that contain one or more impurities. The physical property that is exploited in this process is solubility. If you have made rock candy before, you have actually performed a recrystallization. When making rock candy, such as here in the bottom left, you take sugar and you add it to boiling water. Once you've added enough sugar, you allow the water to cool and you place some string or a stick into the water and the sugar crystallizes out onto the solid support. Of course, we wouldn't be talking about recrystallization if making rock candy was all it was good for. Most of the solid pharmaceuticals on the market today, such as you see here in the bottom right, are purified using recrystallization. Even pharmaceuticals as common as aspirin are purified using recrystallization. The solubility of any compound depends on three things. It depends on the solute, the compound you are dissolving. It depends on the solvent, what you are using to dissolve the solute, and the temperature of the solvent. To connect those three variables, a given solute has a specific solubility in a given amount of solvent and a given temperature. That's a lot of variables to consider when talking about something as simple as trying to dissolve something. Here on the right, we have a graph that shows the solubility of various compounds at various temperatures. The x-axis is temperature, where as you go from left to right, the temperature increases. The y-axis is the solubility of a compound in 100 grams of water. Or as you go from the bottom to the top, more of our compound, in grams, dissolves in the same amount of water. Each line here corresponds to a particular compound. Let us look at 20 degrees Celsius. We see that about 200 grams of sugar will dissolve in 100 grams of water. At that same temperature, we see that about 80 grams of ammonium sulfate will dissolve in the same amount of water. You can see how at the same temperature and the same amount of water, different compounds have different solubilities. A solute, when being dissolved, will dissolve until the solubility limit is reached. At this point, we call the solution saturated. If we go back to our table here on the right, remember that at 20 degrees Celsius, our solubility is 200 grams of sugar per 100 grams of water. That means if you go home and weigh out 100 grams of water into a cup, you can dissolve 200 grams of sugar in there. If you keep trying to add more and more sugar, that sugar will not dissolve and will simply remain a solid at the bottom of your cup. One note before continuing. If you look at the y-axis, this is the solubility in a specific amount of water, 100 grams. If we change the amount of water we use, we change the solubility. Using more water means we can dissolve more solute. Using less water means we can dissolve less solute. This dissolving process is an equilibrium, where our solute in solution is constantly changing back into a solid and then returning back into a solution. Whether our solute favors being in solution or favors being a solid depends on the temperature. For solids, generally, as the temperature of the solvent increases, our solubility also increases. As the temperature of our solvent decreases, the solubility of our solute also decreases. We can see that on the graph here on the right. If we look at sugar again, as we go from left to right, the solubility of sugar increases dramatically. If we take a saturated solution, in other words, a solution that can hold no more solute, and we cool it, it becomes supersaturated. In other words, there is not enough room in the solvent to hold all of the solute. As a result, the solute must exit the solution. When the solute exits the solution, it forms a solid. It forms crystals. This crystal lattice is highly ordered, as you can see here on the right. This regular ordered arrangement is very thermodynamically stable because our solute molecules, represented here by the yellow triangles, fit together very well. This is the reason recrystallization is able to purify compounds. The stability the compound gains by forming a crystal only occurs because the solute molecules really want to stick together to form these structured crystals. If these blue impurities up top tried to attach themselves to the crystal, you can see how, because they are a different shape, they would not fit into the lattice nearly as well as the remaining yellow triangles. Therefore, these impurities remain in solution, leaving us with pure, solid crystal. This is exactly how making rock candy works. If you imagine these yellow triangles as being sugar molecules, when making rock candy you boil water and you add sugar until the water is saturated at the boiling temperature. You then allow that water to cool, forming a supersaturated solution, and so the sugars crystallize out. One note before we continue. Recrystallization is not the same as precipitation. You may have heard of precipitation in general chemistry. Precipitation is when a solid is formed as a result of a chemical reaction. A recrystallization is not a chemical reaction. In a recrystallization, you take one compound, you dissolve it, and then you get the same compound back as a solid. No chemical reaction has occurred. Okay, so in a recrystallization, we know that you have a supersaturated solution and then you allow it to cool. This cooling lowers the solubility of the solute, causing the solute to form crystals. How quickly can you let that solvent cool? It turns out that cooling slowly is much better. Here's why. Here on the left, we have a number of turquoise squares. These squares are our solute. Here in the bottom left, we are beginning to form a crystal, but we still have some of these squares in solution. We also have this red circle. This red circle represents an impurity. Let's see what happens as we wait and watch our solute continue to grow this crystal. We see that one of our squares has left the solution and attached itself to the crystal surface. Oh no, our impurity has now attached itself to the crystal surface. Have we failed now that this impurity has attached itself to the crystal surface? No, because remember, crystallization is an equilibrium. This impurity has attached itself to the surface, but because it is a different shape, it's a different molecule, it doesn't fit very well. So, it returns to the solution. What if it tries again? What if it attaches itself to another place on the crystal? It's still a different molecule. It still doesn't fit well into the lattice. Therefore, it will once again drift away, allowing our remaining solute molecules to attach themselves to the crystal surface and thus finish growing the crystal. Slow cooling allows this equilibrium process to occur, forming large, pure crystals. Let's say we cooled quickly. Well, what happened there? We have the same diagram on the right, and now we're going to have our impurity attach itself to the crystal surface. This time, however, we are going to cool quickly. So before this impurity has time to return to the solution, our solute molecules trap it into the crystal lattice. This is why slow cooling in a recrystallization is much better than quickly cooling. Quickly cooling a solution will result in the trapping of impurities into the crystal lattice, which defeats the entire purpose of performing a recrystallization. Another consequence of this is we form small crystals. Small crystals are harder to isolate and are more likely to be impure. That brings us to the end of this webcast. To recap, recrystallization is a method to purify solid compounds. Recrystallization works by manipulating the solubility of these solid compounds in a solvent. The solubility of solids in a solvent usually increases with temperature. By creating supersaturated solutions, we can cause crystals to form. If done properly, these crystals should be a pure solid compound. A recrystallization functions by dissolving the solid in a hot solvent to ensure that everything possible dissolves, and then slowly cool in order to form our supersaturated solution to allow for pure crystal formation. As our desired compound crystallizes out, the impurities we are trying to remove remain behind in solution.